When nations pursue cutting-edge military capabilities, success often hinges on the infrastructure supporting the technology, not just the brilliance of design. Nowhere is this more evident than in the global race to develop hypersonic missiles. While China has successfully deployed multiple hypersonic platforms, the United States and its allies continue to struggle, shelving ambitious projects, burning through vast sums and falling further behind with each cancelled program. In recent years, the United States military has terminated more than one major hypersonic missile initiative. The most recent to be scrapped was the U.S. Navy's Halo missile project, intended as a carrier killer in the year 2025. This came just 3 years after another hypersonic weapons program was halted. These cancellations reflect more than technical glitches or shifting priorities. They signal a systemic shortfall in the foundational tools required for innovation. At the core of this problem is a stark infrastructure deficiency: the absence of advanced hypersonic wind tunnels. In China, next-generation test facilities like the JL-12 and JL-22 tunnels simulate conditions at speeds exceeding Mach 20 and altitudes nearing 90 kilometers. These enormous wind tunnels allow Chinese scientists to test missile prototypes in a controlled environment that mimics the upper atmosphere's harshest conditions. The United States, by contrast, relies on wind tunnels that top out at around Mach 6, far below the speeds at which modern hypersonic weapons operate. Without sufficient simulation capacity, the United States must resort to launching full-scale test missiles to gather data, an enormously expensive and time-consuming process. In one workaround, engineers modified long-range drones like the Global Hawk to track the flight of experimental weapons, compensating for the lack of ground-based data. But this method is no substitute for the continuous, iterative development that advanced wind tunnels enable. Testing hypersonic vehicles without proper simulation is akin to building a Formula One car and driving it into a hurricane to see what happens. Wind tunnels offer a safer, more efficient approach, generating intense, controlled airflow to replicate extreme conditions. Each airframe design, every material choice and flight control system must be validated in this environment. Without it, even the most powerful computers cannot accurately model the highly unstable aerodynamics involved. China's superiority in this domain was not achieved overnight. It is the result of more than 70 years of sustained effort, often under challenging circumstances. In the late 1950s, Chinese physicists began developing shock tube technology using unconventional and dangerous methods. Rather than importing costly mechanical compressors, they used explosives to generate high-speed airflow. This risky but economical approach, pioneered by scientist Yu Hongru and his team, laid the groundwork for the country's future advancements. Wind tunnel development in China continued through the decades. In 1997, the country completed the world's first detonation-driven shock tunnel, known as JF-10. Later, the JL-12 and JL-22 tunnels would push the boundaries further, enabling tests at record-breaking speeds and temperatures approaching 10,000 degrees Celsius. These facilities are not just engineering marvels, they are strategic assets. Foreign interest in China's wind tunnel capabilities has grown. France once sought to rent access to a facility capable of Mach 10 simulations, only to walk away after balking at a quoted price of €200 million. The European Space Agency attempted to negotiate access to Mach 20 tests, facing a price tag of €500 million. Even the United States reportedly explored options through an intermediary, but was deterred by a projected cost of $5 billion. These high figures are not necessarily intended to sell, they may serve as a polite refusal. The reality is that demand far exceeds capacity, and China's wind tunnels are booked for years. Offering access to foreign militaries would mean sacrificing domestic priorities. As a result, Western nations are left to wrestle with aging infrastructure and theoretical models that cannot match real-world conditions. Historically, the United States led in hypersonic research. As early as the 1950s, American engineers pursued air-breathing hypersonic propulsion. Projects like the X-51A achieved flight speeds near Mach 6. But scramjet engines, needed to sustain such speeds, are notoriously difficult to operate. They must remain stable at thousands of degrees Celsius, requiring breakthrough materials and flight control systems that can navigate plasma fields and intense vibration. Progress has been incremental at best. Russia and China, meanwhile, adopted a more pragmatic strategy. Russia modified its existing Iskander missile to create the Kinzhal, a hypersonic glide vehicle. China took a different route, developing the Dongfeng 17 using atmospheric edge skimming techniques inspired by earlier ballistic trajectories. This approach balances speed, altitude, and control while reducing production and testing costs. With functional designs already deployed, both nations now enjoy a tangible advantage in real-world capability. Part of the challenge for Western nations lies in fragmented project management. In the United States, the Navy and Air Force have separately funded overlapping hypersonic programs, each with its own corporate partners and technology trees. Rather than pooling resources, efforts have often diverged, spreading talent and funding thinly. This redundancy has delayed results and contributed to high-profile cancellations. It is also important to consider the role of national research culture. China's wind tunnel infrastructure owes much to the determination of its early scientists. In 1956, physicist Qian Shueisen, who had trained in the United States, helped establish China's Institute of Mechanics. He invited colleagues, including Gui Yonghuai, to return to China from abroad. These scientists worked with minimal funding and enormous personal risk. When experimental shock tubes exploded during testing, labs were rebuilt by hand. Tragically, Gui died in a plane crash in 1968 while carrying critical missile test data, but the documents survived intact, shielded by his body. His legacy lived on. Just over 3 weeks after his death, China's first thermonuclear missile test succeeded. Over the next half-century, Chinese engineers built on this foundation. The JL-12 wind tunnel team became the first Asian group to win a top aerospace testing award in 41 years. Today, Yu Hongru, now 97 years old, continues to advise young scientists, insisting they take the stage as leaders of the next generation. By contrast, Western programs have suffered from both a lack of long-term continuity and erosion of fundamental research capabilities. Much of the original expertise in supersonic and hypersonic systems has retired without replacement. Even once great facilities capable of Mach 2.75 airflow have struggled to maintain relevance. Without a new generation of talent and investment in basic science, the West's ability to develop next-generation missile systems remains constrained. Ultimately, hypersonic weapons are not merely a function of theoretical brilliance or software sophistication. They are forged through decades of experimentation, in facilities where models are pushed to their limits, refined, and pushed again. Computers can simulate ideal conditions, but only physical testing reveals the chaos of real-world airflow at many times the speed of sound. The East has built that infrastructure. The West for now has not. When observers ask why China continues to roll out hypersonic systems at a pace others can only watch, the answer is not found in code or blueprints. It lies in the humming chambers of a 265-meter-long wind tunnel near Beijing, in the scorched debris of an improvised shock tube from decades past, and in the briefcase saved by a physicist who believed in building something greater than himself. Success in this domain does not come from inspiration. It is built, painstakingly, from the ground up, generation by generation.